Hi everyone, welcome to our talk. I am Mingzhe, a PhD student from the University of Utah. Today, I would like to present our work that compares Morse complexes using optimal transport. Our collaborators include Wang, Carson and Austin Yang Li from the University of Utah, and Tom Needham from Florida State University. First of all, we would like to introduce some terms for background information. For a 2D scalar field, we can visualize it as a terrain, where the height represents the scalar function value. There are three types of critical points in the scalar field, namely maxima, minima, and saddles. Maxima and minima in the scalar field will appear as peaks and pits in the terrain. All non-critical points are considered as regular points. Here, we focus on Morse complexes on 2D scalar fields. A Morse complex partitions a scalar field into multiple cell regions based on gradient behaviors. Here is an example of the descending manifold of the Morse complex. Each cell region is assigned a unique color. At any regular point, we can integrate the gradient in both ascending and descending direction to get an integral line. The integral lines of all points in the same cell region end at the same maximum. The cyan line draws the boundary of these partition regions. A Morse complex consists of critical points, partition regions, and boundary lines. We call the boundary line the 1D skeleton of the Morse complex, or the Morse graph. Our main contribution is to provide a set of distances to compare Morse graphs. There are previous works comparing Morse complexes, most of which compare the graph derived from Morse complexes. Feng et al. Compare feature graphs for matching critical points. The work by Thomas and Tarja in 2013 and Narayana et al. In 2015 both compare extremon graphs, which are the simplification of Morse and Morse map graphs. Our work compares Morse graphs using tools from the optimal transport. Our proposed distances are based on optimal transport. Here is a high-level overview. We treat all Morse graphs as networks by sampling points along the edge. We then model the network graph as measure networks in the form of VPW. P denotes the probability distribution over the node set V. W encodes the pairwise relation between nodes. To minimize OT distances, we must find the optimal coupling matrix. A coupling matrix between networks represents a joint probability measure of the product of two node sets. Each non-zero entry in the coupling matrix indicates the probability of the matching between the corresponding nodes in two networks. In other words, OT distances not only tell the dissimilarity between two Morse graphs, but also provide a matching between nodes from two Morse graphs. Such matchings will help us understand how these distances compare Morse graphs. We skipped some technical details for simplicity. Please refer to our paper for the formal definition. Let's go through all the OT distances that we apply to compare Morse graphs. The first one is the Wasserstein distance. The coupling probability C is weighted by the squared Euclidean distance between points. The intuition is that matching faraway points gives a high cost. In the example below, if we try to match node I in the left graph to node J in the right, the loss of this matching will be the square of the x-coordinate difference adding the square of the y-coordinate difference, which is 1.3. Another distance is called the Gromov-Wasserstein distance, or the GW distance. We use the shortest path between nodes to describe the pairwise node relation in the graph, which is given by the graph structure. The optimizer of the distance tries to find the minimal intrinsic graph structure variation between matched points. In this example, the cost of matching node I to J and node K to L is given by the square of the distance of their shortest path. Given the shortest path between I and K is 1.8, and between J and L is 0.9, the last term should be the square of the difference, which is 0.81. The fused Gromov-Wasserstein distance, or the FGW distance, incorporates the cost from both Wasserstein distance and the GW distance, which enables it to perceive the change from both geometric location and intrinsic graph structure. The alpha parameter balances the weight between the two terms in the distance. Optimal transport has a variation that allows certain probability to be ignored in the matching. called partial optimal transport. For instance, in the bottom right example, distances using the optimal transport will have to match some node on the left to the noisy nodes on the right. Using partial optimal transport, noisy features can be ignored in the coupling, making the matching more reasonable and robust to noise. All previous distances have their variations using the partial optimal transport, namely the partial Wasserstein distance, the partial Gromov-Wasserstein distance, and the partial fused Gromov-Wasserstein distance. We now present the results of our proposed distances by using the color correspondence to demonstrate the matching between two networks from Morse graphs. We assign colors to node in the source network based on a color map. In the target network, each node will have the same color as its matched node in the source network. Recall that the Wasserstein distance and the PW distance compare the geometric locations of points. The GW distance and the PGW distance compare the intrinsic graph structure. The FGW distance and the PFGW distance incorporate both. Among the top three distances, the color correspondence in the result of Wasserstein distance and the FGW distance show reasonable structural alignments with the source. The result using the GW distance display wrong correspondences. For example, the bottom left structure of the source is matched to the top right structure of the target. This is because GW distance is unaware of the symmetry of the data. The bottom three images show the color correspondences results of partial optimal transport distances. All nodes ignored in matching are shown as hollow circle. As indicated by arrows, all partial optimal transport distances can ignore some noisy features that deviate from the source. We further demonstrate another result using a scientific simulation dataset called heated cylinder. We demonstrate the result of the PFGW distance, which incorporates the encoding of geometric location, graph structure, and ignoring noises. Regardless of structural changes between the source and the target, the color correspondence looks smooth and reasonable. Besides, the additional edge that appear in the target network is successfully ignored in the matching. There are more results using data from scientific simulation or the real world. Please refer to our paper for detailed analysis of these distances. In conclusion, our major contribution is to apply a set of optimal transport distances to compare Morse graphs. In the future, we would like to extend our work to Morse-Mel complex and its variants. Besides, the coupling results from the optimal transport can be applied for Morse complex-based feature tracking.